It's just going to be a little more complicated because we have fractions. I just dropped my laptop. That was not... Hey everybody, this is chapter 12, Solving Quadratic Equations. This is really good stuff. I'm going to cover the entire chapter in this video. We're going to spend most of our time on the first 3 sections, each of which describes one method that you could use to solve a quadratic equation. I'm also going to show you how to do it on the calculator as well. And then at the end, we'll briefly mention section D. That's really just about word problems, so I don't have anything else to say about it other than you should be able to solve word problems using one of the methods covered earlier in the video. We'll start with something that we know, a little review here. We have previously studied linear equations before, and the book here says they have only one solution. Now, we saw some special case linear equations when we studied them, which had either no solution or infinitely many solutions. That's true. However, if you remember what those looked like, they were always going to have the x terms cancel out, and so we would have been left with either some number is equal to the same number, which would have indicated infinitely many solutions, or we would have seen some number equals a different number, which would have indicated no solution. So the format that we see here of ax plus b equals 0, where a is not equal to 0 itself, that couldn't have happened in either of the special case equations, because in those the x terms would have canceled out, meaning that we had 0 x's. But here we're saying we cannot have 0 x's. We must have some other number of x's. Anyway, all of that is to say that if we have a linear equation in this form of ax plus b equals 0, there's going to be only one solution. Specifically, it's going to be x equals negative b over a. And we've got an equation as an example down here. And so we add 2 divided by 3, we get our answer 2/3. By the way, it's called a linear equation because if we were to graph y equals ax plus b, that's going to give us a line. Now we move into new stuff, quadratic equations. And we see that they're going to have the exact same form as the linear equation in the blue box up there, where we're going to set everything equal to 0. And that wasn't something that we necessarily thought about doing when we studied linear equations, but it's going to be a crucial step for us when we're solving quadratics. So we're always going to take all of our terms now and move them to one side and get a 0 by itself on the other side. And for this equation to be considered quadratic, this a term, which is now the coefficient of x squared, that must not be 0, because if that were equal to 0, that first term would go away, and then we would be left with a linear equation rather than a quadratic equation. Okay, so we've got ax squared plus bx plus c equals 0, and a is not equal to 0 itself. Now, a quadratic equation could have 2, 1, or no real solutions. And don't worry about this word real. You remember earlier in the course, I mentioned that there are imaginary numbers out there. That's something you're going to study in a future course. Everything that we do will be real here, but we're talking about, like, if I had x squared equals to negative 1, that's a quadratic equation because it has an x squared. However, there's no number, or there's no real number that when I square it, it gets negative, right? Positive times a positive is a positive, negative times a negative is also positive. So this equation is impossible unless we allow imaginary numbers. But that's not the topic of this video, so I'm not going to talk about it anymore. And yes, we could have a special case quadratic equation that has infinitely many solutions, just like we had special case linear equations, but we're really going to be focused here on just the normal everyday quadratic equations rather than the special ones. So here's an example of one that we can solve. And we see that we can verify here that x equals 2 is a solution to that equation, because when I put in 2 for the x value, I get 0 out. And so yeah, that whole thing is equal to 0. Same thing happens when I put in negative 5 into that expression. So in this case, the 2 and negative 5 are both solutions sometimes called roots of the quadratic equation. We could similarly verify that -1 is a solution for this equation, and then the third example is actually the one that I just showed a moment ago that has no real solution. So that's great that we can check whether an answer works, but how can we find out what that answer is if we didn't know it? Well, that's what we're going to talk about in this video. We've got 3 methods that we can use, and the first one is using factorization. So we've been talking about factoring now for a really long time. The idea here is that if we have a product of 2 numbers and their product is equal to 0, well, then that means that one of those 2 numbers must have been 0. Maybe they were both 0. 0 times 0 is 0, of course. But at least one of them needs to have been 0. And so we can use that if we have a quadratic that we can factor. So check this one out. I've got x squared equal to 3x. First step, like I said earlier, we're going to bring everything over to one side, setting it equal to 0. Now we're going to factor. Those two both have a common factor, which is x. So we factor that there. And then we just take each of the factors and set it equal to 0. So on the left, I have x equals 0. That's easy. It's already solved. Nothing to do there. On the right, I have x minus 3 equals 0. Solving that, we get x equals 3, and we have 2 answers. Now, I wrote a big note over here. It says, don't divide. What I mean by that is in the first step, you would not want to divide by x on both sides. If you did that, you would just get x equals 3, so you'd still get one of the answers, but we'd be missing the other answer. And if you think about it, if x were equal to 0, would we have been allowed to divide by it? Well, no, because then we'd be dividing by 0. So we're never, ever, ever going to divide when we're solving these equations. We're always going to move things to one side and then factor. All right, and this idea is called the null factor law. I didn't mention that before. I've seen it be called the zero product property and whatever. It's got a million names. In every different math textbook will call it something else. But the point is, we're going to bring everything to one side, other side set equal to 0. Then we're going to factor whichever side has our x's and x squareds on it. And then we're going to solve each of those factors being set equal to 0.
I've just been sitting here editing videos, and I realized that I left out one important thing. See, in the video I mentioned that a linear equation is so called because when we graph it, we get a line. But I failed to mention the linguistic connection for quadratic equations because when we graph them, we get a parabola. So the word quadratic comes from the Latin quadratus, which means square. And you see the connection now to x squared, I hope. The word parabola, on the other hand, its history is a little bit more complicated, and I'm not even 100% sure why we use the word. All I can say is that the word parabola comes from ancient Greek, and it's been in use in mathematics for a long time, and I think the word has kind of undergone a few different meanings throughout history. When you get into really advanced geometry, we talk about spherical, hyperbolic, and parabolic geometries, and it has nothing to do with parabolas in any sense that I can understand. So don't think too hard about where that word comes from, but I don't know. There we are. Anyway, enjoy watching.
So let us quickly look through some examples together. Here we have a quadratic equation. We're going to set everything equal to 0 by bringing the 28 over to the left-hand side, and then we're going to factor. So we're looking for 2 numbers that add up to +3 and multiply to -28. Those 2 numbers are going to be +7 and -4, and then we set each of those factors equal to 0. So we have x +7 equals 0 and x -4 equals 0, and then we solve each of those, and we get x equals -7 or x equals 4. In this case, it's kind of as simple as just saying like, oh, I'm going to change the sign from what I see here to what I see there. But that little shortcut only really works when you have one x plus or minus a number. We'll see in some future examples that, we may have to do some other work in addition to that. And then we could check our work, of course, by taking -7 or 4, putting them back into the original equation, and making sure that we get 28. Okay, this one's going to be a little bit harder because I see 5x squared, which means the factoring is going to be a little bit more challenging. But just like before, we're going to bring everything over to the same side and then we need to factor this. So we can predict that it's going to be 5x plus or minus something and 1x plus or minus something, and this c value over here of -2 is telling me that I should have only 1 and 2 as my constant terms in the factoring. So with a little bit of trial and error, we can work out this here. So we see the grouping method was used in this case, but however you want to do it, you should be able to factor to that without too much difficulty. And then we set each of those equal to 0, and we solve. So again, from this term, it's really easy. We just change it to -1 to +1. Great, but we need to be careful here. We need to actually set that equal to 0. So we subtract 2 and then divide by 5. Notice just a moment ago I referred to this -2 as a c value, and that's because I'm thinking about ax squared plus bx plus c. And especially when we get to the quadratic formula, which is the third method that we'll see in this video, it's really, really important to be able to identify your a, b, and c terms. So in this case, a is 5, b is -3, and c is -2. So we want to just get used to thinking about that, all right? And here's one more that looks terrible. Oh my gosh, there's 2 fractions. It's totally fine. We've seen proportions before. Again, I like to do these a little bit different than how the book does. I would just cross multiply. So I'm doing 2 times x minus 2 and set that equal to x times 6 plus x. So you have that right there. The book is just getting the same denominator on both sides and then ignoring the denominator, which it's fine if you like to think of it that way too, whatever. Anyway, from here, we're now going to distribute. So we're going to bring that 2 in, and we're also going to bring that x in. And that gets us this nice quadratic equation here. I see the x squared term. So we bring everything over to one side. And then from here, that's actually very easy to factor all of a sudden. That's just going to be x plus 2 squared. I see the shortcut there of a squared plus 2ab plus b squared. And that tells us that we only have one solution to this one. -2 is the only answer. Last one for factoring, and we kind of have a few different ways that we can think about this one. So we do notice here that the least common denominator is equal to x times x plus 6, because this last term over here is just divided by 1, so whatever. So what the book's going to do is it's going to give everything that same denominator. So this first fraction needs to have an x plus 6 in the denominator, so we also include an x plus 6 in the numerator. Second fraction is missing an x in the denominator, so the numerator gets an x. Third fraction is missing both x and x plus 6, so it gets it in the numerator and denominator. And then we notice that all 3 of the fractions have the exact same denominator, so that means we can just essentially multiply by that common denominator everywhere, and the numerator will be all, the numerators will be all that's left. So we have an x plus 6 from that first fraction right there, and then we have a 4x from that second fraction right there, and then that's equal to the x times x plus 6 from the third fraction. Of course, you are also welcome to, for example, combine the first 2 fractions, the 2 on the left. You could get them a common denominator and then put them together into one fraction. And then from there, we could cross multiply x times x plus 6 times 1, set that equal to 1 times 5x plus 6. And again, we're getting to the exact same place that the book's method was, so whatever. Anyway, from here, now you can see we have the x squared once we distribute on the right-hand side, which means we have a quadratic, so we move everything to the same side. And then we just try to factor that. Again, that's not too difficult to factor, so we get 2 answers, -3 and 2. So now we're going to see 2 methods that we can use when we can't factor. Now, I really only need you to know one of these 2 methods, because they'll both always work. It just kind of comes down to which one you find to be easier. The first one's called completing the square, and I'll be honest with you, it's not my favorite thing. I really don't like using this method for solving quadratics. Some other math teachers I know find that to be very peculiar, but That's just my personal preference. I love completing the square in other contexts. It's really important for like if you're ever working with circle equations, which I believe is on the SAT, you need to know how to complete the square to work with those. And it's really helpful for when we are changing a quadratic function into something called vertex form. That's something we'll talk about later on in the course. I just don't like it for solving quadratic equations, but I'll show it to you. I'll give it a fair shot, and if you like it, then you can totally use it. Me, I just use the quadratic formula. But anyway, here's how we can complete the square. So the idea is we're gonna do some special math, which I'll explain in a moment. But our goal is to get on one side of our equal sign a perfect square, and on the other side we'll just have some number. So like as an example here, if we had just x squared equals some number k, then depending upon what k is, we would know how many solutions the equation has. So if k were some positive number, then there should be two solutions to this. We'd have plus or minus the square root of k. So if that was like x squared equals 16, we could have plus or minus 4. If k happens to be equal to 0, then there's only going to be one solution. It's going to be 0 squared equals 0. So then we'd just have that one. But if k was a negative number, then we would have no real solutions. We kind of talked about that earlier. So here's two examples. And we actually kind of saw one just like this a moment ago when we had x plus 2 squared is equal to 0. So if we had x minus 3 squared equals 16, well, let's just take the square root of both sides. That's going to get us x minus 3 equals plus or minus 4. And then we'll just add the 3 to both sides. And we'll get either 3 plus 4, which is 7, or 3 minus 4, which is negative 1. On the right, we can take the square root of 11. So x plus 2 is plus or minus square root of 11, and then we'll just subtract 2 from that. So we get x equals negative 2 plus or minus the square root of 11. And yeah, that's some decimal, but I don't have a calculator handy, so this is a perfect answer. I love it in that form. Embrace exact form, children. Now, something like this, since its two answers ended up being like integers, yeah, you know, we could have expanded. We could have done x minus 3 squared and gotten x squared minus 6x plus 9 and set that equal to 16. And then we could bring the 16 over to the left-hand side, subtracting that from the 9, and we get minus 7 equals 0. And then we could factor that, and we could see that we're going to get x minus 7 times x plus 1. And then, yeah, when we solve each of those, we get the two answers that we got. But since it was in this nice form of something squared equal to some number, it's a little bit faster in this case just to take the square root. All right, now what happens if the equation isn't set up in this nice form for us, where we already have something squared on the left? So there's a process to doing this. So here's an example of it. So here's our quadratic equation right here. We're going to solve that using completing the square. So our first step when we complete the square is we need to make sure that the coefficient of x squared is 1. And you see here we have 1x squared. That's great. If it were not 1, then we would have divided by that number to make it 1. We'll see that in the next example. Okay, so we got 1x squared plus 8x minus 4 equals 0. Great. We're now going to move the constant term to the other side. So it's no longer set equal to 0. And then this is the most important part now. We're gonna add some mystery number here so that this entire left-hand side is a perfect square. So that it is x plus or minus something all squared. But since it's an equation, whatever we add to the left, we have to also add to the right. Now, in this case, the special number we need to add is 16. Now, why is it 16? Well, first of all, if I want to get x plus something squared out of this, then we can tell when I do x times x, I get x squared. That's great. This middle term here, 8, that's going to be x times this mysterious number times 2. So that kind of tells me what that mysterious number needs to be. It needs to have been a 4. And then in the box, what's left over is going to be that number squared. So what we end up doing in practice, because that felt like a little too much like a guessing game to me, we're just going to take whatever the coefficient of x is, we're going to divide it by 2, and we're going to square it. And that's always the number that's going to go in the box. So half of 8 is 4, square it, we get 16. There we go. Now we're ready to use completing the square, because the left-hand side, that whole thing just becomes x plus 4 squared. The right-hand side, 4 and 16 is obviously 20. Now I take the square root of both sides. X plus 4 equals plus or minus the square root of 20. And then we can subtract that 4 from both sides. It gets us right there. Now the square root of 20, we know that that's the square root of 4 times 5. And of course the square root of 4 is 2. So we can rewrite that as negative 4 plus or minus 2 times the square root of 5. Amazing! Let's see another one. So here, oh, I'm sorry, this one also has a coefficient of 1 for x squared. So we don't need to divide. In this case, sorry, the next example will have that. But we see everything else is the same as before. So we move the 1 over to the right-hand side. And then we're going to take half of 6, which is 3, and we're going to square it. 3 squared is 9. So we add 9 to both sides. So now all that we need to do is factor this expression. That's easy. We have x plus 3 squared is equal to 8. Taking the square root, x plus 3 is plus or minus square root of 8. And then subtracting 3, we get that as an answer. Of course, 8 is the same as 4 times 2, so we can simplify that radical and get negative 3 plus or minus 2 times the square root of 2. And you could leave it kind of tied together by that plus or minus like we have in this box, or you could rewrite it as 2 separate answers, whatever makes you happy. Now let's look at one where we don't have 1 as the leading coefficient. All it adds is 1 extra step, and it's a new first step. So in this case, we're going to divide the entire equation by 3 to get 1x squared. 6 divided by 3, that's 2. Okay, we have a fraction now as our constant. We get minus 2/3. That's annoying, but the rest of the process is going to be identical to what we did before. So we're going to move the 2/3 over, and then we're going to take half of 2, which is 1, square it, and then add that to both sides. This is now a perfect square trinomial, and it will always be a perfect square if you take half of the constant term and square it. It's amazing. So now that's x plus 1 squared. And that's going to be equal to, well, 1 is the same thing as 3/3 plus 2/3 is 5/3. Oh, by the way, when we factor the expression, because we've kind of created this expression to work out nicely, the value within our parentheses when we factor is always going to be half of that number. In all of the previous examples, you'll see that it was always half of the b value, and it always will be. Okay, so anyway, there we take the square root. Great, x plus 1 is plus or minus square root of 5/3, which means x is equal to negative 1 plus or minus the square root of 5/3. Now, if you want to rationalize the denominator, then we can break up this 1 square root into 2, so a quotient of square roots, and then we can multiply the numerator and the denominator by the square root of 3. So that'll get us negative 1 plus or minus root 15 over 3, and then we can rewrite the negative 1 as negative 3 over 3 to get a common denominator, and that's how we get this final answer down here. Okay, so that's completing the square, and you know, it's not that bad, even when we have to divide by 3. You know, it's fine. You might just have some fractions that you need to deal with. It's probably the worst case is really when you have an odd number there as your b value, because then when you take half of that, you will have a fraction, and then you'll have to square that fraction, and then you'll still have a fraction that you'll have to add to both sides. That gets especially annoying. So in that case, I would say the completing the square is definitely not the fastest way to do it. You would definitely want to use the quadratic formula, which I'm about to show you. But if you do have an even b value, I should say an even b value after dividing by the a term. So we should be looking at that 2, not the 6 above. Sorry. But if you do have an even b value once you have 1x squared, then completing the square is really not that hard and doesn't take that much time to do. Anyway, that being said, let's look now at the quadratic formula. All right. And look, the book agrees with me. Completing the square can sometimes be rather tedious. Ha. Anyway, if we've got our quadratic equation written in the form that we saw earlier, so everything's set equal to 0, then x is equal to this expression here, negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Some of you may have learned this as a song in previous years. Pop Goes the Weasel. I'm not going to sing that to you now, but you can look it up or ask a friend if you want help memorizing it. So let's take a look at that with an example here. 2 examples. First one, what is a in this case? A is 1, b is negative 2, c is also negative 2. We need to know that if we're going to use quadratic formula. So when you're first practicing this, I really recommend actually writing down a equals b equals c equals so that you can keep track of what the heck you're doing. So we do the work. X is equal to negative b. Negative b in this case is going to be positive 2. So we see that there. Plus or minus the square root of b squared. So that's going to be negative 2 squared, which is positive 4. And then minus 4 times a, which is 1, times c, which is negative 2. Multiply those 3 together and you get plus 8. 4 plus 8 is 12. And then from here, it's just a matter of simplifying that expression. We note that 12 is the same as 4 times 3. So we can take the 4 out of the radical, giving us 2 plus or minus 2 root 3 over 3. But now every term has a factor of 2, so we can cancel, leaving us with just 1 plus or minus root 3. In the second example, what is a, what is b, what is c? A is 2, b is 3, and c is negative 4. So x is equal to negative b, which is negative 3, plus or minus 3 squared, minus 4 times 2 times negative 4. That's 4 times a times c, all divided by 2 times a, which is 2 times 2 in this case. And then we simplify stuff. So we have negative 3 plus or minus square root of 9. And then negative 4 times 2 times negative 4 is plus 32. That's just going to be a square root of 41. That's a prime number, so we can't simplify that any more than it already has been. So what I really like about the quadratic formula is, well, to put it simply, it's a formula, whereas completing the square is a series of steps that you need to memorize. With the quadratic formula, yes, you need to memorize this formula, but once you have that, it's pretty automatic what you need to do for every single equation. It's the same thing every time. So yeah, I don't even have any other examples to show you here because it's just figure out what A, B, and C are and then substitute them in the appropriate places into that formula and you're good to go. Okay, so to conclude here, if we're solving quadratic equations, we should definitely try to factor. Okay, factor if you can. It's more certainly more efficient and faster than the other 2 methods. But if you're having trouble with the factoring, then you can try completing the square or the quadratic formula, whichever one you prefer. Okay, there are also at least 3 different ways that we can try to solve a quadratic equation on our calculator as well. So let's look at those. First, we'll go from the calculator screen itself. Here's what we might do. We'll press menu, and it certainly feels like we're doing algebra. And I want to direct your attention to polynomial tools. And we're going to try to find the roots of a polynomial. Remember before we saw that the roots basically means the solutions of the equation, right? And then there's some technical differences between those, but for our course, yeah, they're roots, solutions, same thing. So if we were to click this button here, find the roots of a polynomial, It's going to ask you for the degree of the polynomial. Degree just means what's the largest exponent in the polynomial or in the equation that we're trying to solve. We're doing quadratics, which has x squared. So the degree is going to be 2. We're finding the real roots because, again, in our course, we're not even worried about complex roots. So we're just going to press OK. And then it asks us for a with a little 2 next to it, a with a little 1 next to it, a with a little 0 next to it. Notice up here, a2 is just our a value from the quadratic equation before. a1 is our b, and a0 is our c. So to solve the equation that we just looked at last, I could type in 2, 3, and -4. So I'm just putting in the coefficients, just the numbers. I don't worry about the x's or anything. I press OK, and then I just need to press Enter. And it's given me 2 decimals. However, it's easy to check and see that these 2 decimals are the approximations of the exact answers that we got before. Great. Second option that we could use is to press Menu, Algebra, and now, okay, this first one. Now, I'm using a calculator that is not a CAS, stands for Computer Algebra System. Your calculator might say somewhere near the top of it, capital C, capital A, capital S. In that case, you're going to have in this submenu here something that just says solve. If your calculator does not say CAS, then it will just say numerical solve. That's the best that you can do. If you choose that, or if you choose solve, we can then type in the equation that we wanted to solve. And I think we talked about this back with linear equations. At the end of the equation, we need to type comma x to let the calculator know what is the variable that we're solving for. And if I press enter, my calculator using nsolve only gets me one of the answers. If you're using solve on the CAS, then it will get you both of the answers. And the third option is to go to a graph and graph the function. So we ignore the equals 0 part, just type in 2x squared plus 3x minus 4. We get this graph of a parabola, and then we want to know when is that graph equal to 0. So we're going to go Menu, Analyze Graph, and then just find the zeros. We've done stuff like this before. It's asking for a lower bound, so I move the line somewhere to the left of a 0 and I press enter. It now is asking for an upper bound, so I move it to the right of a point, and I see immediately as soon as I pass that particular 0 that it gets me this answer, -2.35. I'm just going to grab that and move it over. And then I can do the exact same thing again to find the second answer. So we get the decimals that way as well. What's my preference for these various methods? Okay, obviously the graph is the one that takes the most time to do. However, if you wanted to do that on an exam, then you'd be able to draw the picture and that could actually show me what you did. So I like the graph because you can get partial credit for it. And I also like the graph because using the graphing method will work for many other types of equations as well. Whereas using the polynomial root finder, that only works for special types of equations. And if you're using, well, if you're using solve on a CAS, then that'll work for everything. But you can't get partial credit if you type in the equation wrong, because I won't have a clue what you did. And then obviously nsolve on a non-CAS, you're just missing solutions. So if you don't have a CAS, then don't use nsolve. Just use the graph or the polynomial root finder. Polynomial root finder is faster than the graph. Again, however, when we get into other weird types of equations, the graph is the way that you're going to want to do it. It's going to eventually be the only option that you have. So no harm in getting used to it now. One other thing I should mention about the calculator methods. First of all, you'll notice that mine was giving me decimals for all these answers rather than giving me the exact answers. I believe on the CAS that the solve function will give you the exact ones, but generally the polynomial root finder and the graph do not. They give you decimals. So since I, as the teacher, I know that you have access to this technology, two things I might do. First, I might specifically ask you for the exact value of the answer, which is going to require you to use either completing the square or the quadratic formula. Or I might give you the answer in advance, and I would say, hey, show that the answer to this equation are these two particular values. And then you'd have to write down the work that justifies that that's the answer. At the very least, the calculator is a great way for you to check your answer pretty quickly if you've done your work by hand. All right, now that's how to solve quadratic equations. Like I said, we've got to know, you've got to know at least one of those two. Better if you know both, but if you only know one, you'll be fine. And then factoring is a good shortcut. And also, I mean, look, if you're not good at factoring, then this course is going to be a struggle for you. Let's just be honest. So hopefully you're comfortable with that for the easier problems. Now, just to briefly discuss section D, which is all about word problems. I'm not going to do any examples from that because every single word problem is going to be different. And it's going to require that you read and that you think about it. But eventually you're going to get a quadratic equation out that you will solve using one of the techniques that we just discussed. So what are we going to do? Carefully read the question until you understand the problem. Sometimes drawing a picture is going to be very helpful for you to do this. You're going to want to get a variable into your work somehow. You could use X, you could use any letter that you want. Maybe sometimes, using W might make more sense if you're dealing with like the width of a rectangle or something. But point is get some variables out there, okay? And then write down an equation. At that point, just use one of the techniques we just talked about, solve the equation, check your answers, make sure that they're reasonable. Sometimes the quadratic equation that you get might give you like a positive and a negative answer, but the word problem might be about, say, a distance or something that could only be positive. So in that case, you would have to ignore the negative answer. So you need to really make sure that your answer is reasonable and make sure that you are actually responding to the question itself. Remember that you might, in some complicated thing, you might have a quadratic equation for x, but you ultimately might be asked some question that's not about x directly. It might be something about, I don't know, 2x or something like that. So just because you solve the equation doesn't mean that you've answered the question. So you want to always, the reason that it's helpful to write your answer to the question in a full sentence is not just to make you like practice writing or something like that, but it's so that you are actually mindful of what you're doing. And forcing yourself to write down what the answer is in a sentence will force you to consider whether or not you have actually answered the question that was asked. So something to consider there. Okay, so that's all of chapter 12 in one video. Seems like a lot, but we're going to spend a little bit of time on this together. We're going to solve a lot of equations using the various techniques because I need you to be good at that. I need you to be able to do it fast as well. And then we'll look at some word problems. We'll practice our reading and our problem solving skills, but after we feel a little more comfortable solving the equations themselves. Because once we get up to those word problems, I want the equation part to be boring, and I just want you really focused on, coming up with the right equation for the problem itself, and then not have to worry about whether or not you know how to solve the thing. So that's it. I should mention we discussed quadratic equations here. We did not discuss quadratic graphs, except for that one example we saw in the calculator, but they're going to come back. Don't worry. We'll deal with parabolas in chapter 20 of the textbook. So we got a little bit more we got to do before we come back to them. But don't worry, quadratics are certainly not going away, and they will absolutely feature prominently in many future math courses in your life as well. So yeah, I hope you learned some things, and don't sing that stupid song in front of me, or I'm going to take off 600 points in your next test.